All right, everybody, welcome to Air Science. We're going to continue with the notes. Let's go back to it. Oh, look at all this stuff. And move on to the next topic. So we should have tackled weathering within lesson 2, all the stuff that you did the week before February break. Weathering would include all the breakdown of rock. So take the Earth's bedrock and let's start beating it up, breaking it down into smaller and smaller bits. Small rocks down to smaller particles, boulders, cobbles, pebbles, sand, silt, clay. All of those referred to as sediments. And that's what we're going to get into today with erosion, is the movement of the sediments. So remember, the idea is weathering, erosion, and deposition. Those three things. Weathering breaks down the rock. Erosion moves those small rocks or sediments. And deposition will be next. We'll be dropping those off. I'm not going to do an erosion lab this year with all the online stuff. I don't think it would work very well online, and it'd slow us down a bunch. So let's talk about it a little bit. I'll throw together one of those little quizzes, and if I can figure out how to have you play with Google Earth a little bit, I might do that, but that might be a little ambitious. We'll see. So I'm going to go in a slightly different order. Let's jump right in. Let's look at some rivers and see what's going on here. So for reference, I'm down in the Mississippi, and what you should notice, I mean, the main river channel is pretty visible, right, with that brown. But as you go around, you can see that this whole entire area is just littered with all of these different former paths of the river. In fact, they occupy this whole entire region. You can see the dark green here. That'd be where it's a little bit more hilly, where it's light green here and flats. I'll use a ruler. From there to there. Whoop. Okay, there we go. From there to there, we'd call the floodplain. So now this river is very controlled. They try to avoid floods by controlling it and managing it a lot more than it was before humans showed up and developed all this technology, right? But nonetheless, this area would be the area that would, during high water times, flood and then recede back into a channel and maybe a different channel. And then also through time, these channels are very dynamic. They change, they change, they change, they change. That's just kind of how it is. And if you're going to try to settle this area, farm this area, that change has to be part of the equation, right? So this, what we call them, these rivers that go back and forth and back and forth and around and around and around and around and around are meandering rivers. Meander. And I always pick on somebody in class. I can't do it this year because it's a weird year, but I pick on somebody that is always late to class. And I say, well, that person meanders because they go from their last class to their locker, to their friend's locker, to the bathroom, to the cafeteria, and then eventually make it to their next class, right? That's a meandering path. These are meandering rivers that go back and forth and back and forth. They really only happen on, excuse me, reasonably flat plains. I mean, it can't be flat. Water's not going anywhere if it's flat, right? This is pretty darn flat, though, because if there's more of a slope, water's not going to screw around. It's just going downhill, right? Once you get down to it being reasonably flat, you get these meanders. All right, so what I want to look at, this is pretty good right here. I was going to do it right up here. I want to look for signs of where is erosion happening and where is deposition happening. This white that you see would be sediment. That'd be fresh sand, silt, whatever it might be in that environment, right? Where are you noticing that it is on these curves? This is going to be a big thing that we got to get down with these curves, is where is there erosion and where is there deposition? Well, if I see sand, that would be deposition. That's sediment being dropped off. And if you follow the path of the river, the water's flowing this way. If you follow the path of the river, maybe we're noticing where it is. It's always on the inside of curves. So take this water here. Basically, let's look right here. If this water wants to go in a straight line that way, it's going to go pounding right into the side right there. So as it comes around, the speed on the outside is going to be faster, whereas the speed of the water on the inside is going to be a little bit slower. I know we got people in the school that fish and you've probably noticed this, that the slower water, and maybe shallower water because of depositions on the inside of bends and on the outside would be faster. The black hole down there, for example, it's pretty evident. So what we end up seeing, and I don't know if we'd really be able to see any erosion or, oh yeah, look at this. You got trees falling into the water. In fact, there's going to be a regions question that asks about where is it likely that a tree is going to fall into the water? And the reason that happens is because the bank is being eroded. The soil that the trees are in is being removed by these natural processes. And as you're on the outside of the curves, that's where it tends to happen. The slower water on the inside then will drop that sand off. So let's picture it. Right where that fallen tree was, that soil got picked up, carried downstream, and now it goes banging down into this side, and maybe there's, signs of erosion. So if you see exposed rock, dead trees, this is all an area where sand will be carried away. But that sand from upstream up there gets dropped off on the inside of these curves. Yeah. All right, and you can see all these former channels. So these things, like through time, will change and change and change and change. Okay. And if we had to draw it out, I don't know how thoroughly I'll have you do the notes because I think it'd be a pain to write as much as I usually do in Cami. But the general trend is let's say this is like an early one. In fact, it is because there's the old. So this used to be a big old bend right there. Now it's reasonably straight again. So here's the process. It begins as a small curve, and then I know this is all right now. This is 2016, June of 2016 imagery. But we can look at it as the different phases of these things. If we could jump into a time machine and watch this river for thousands of years, then we would see all of these changes happen over all these different sections of the river. So start as a reasonably straight, turn into a larger curve right there. I saw a couple of pretty big ones. I mean, you can get them eventually where they're almost like that one, like cut right through on this smaller river over here. Big meander right there, all the way around. So what's eventually going to happen is that cuts off and gives you a straight shot again and leaves that old river channel isolated, which will then like either stay filled in with water for a while. That one's pretty dried up. Let's see, that one's pretty dried up too. If they stay filled in with water for a little bit, like on this main channel, there's a whole city built on this one. So there's former Mississippi River. It's now cut off. That meander this river would have been like a big loop over here and all the way back around, but eventually the water cut through right there and took a shortcut, basically. Water's always going to take the easiest path and abandoned this thing. We call this, and I'll write it in the notes so you see all these terms. We call it an Oxbow Lake. Kind of a weird term. This horseshoe shape. People always want to call it a horseshoe lake, but it's not. If it's a big river, they can be pretty big. Like here's a whole town like built on one. You could boat on this thing. Let's see. Let's go into the town. That's pretty big. And it's a lake, but it's really a former river that's been cut off from sediments. Yeah. And cut off from not only sediment, but also the fresh water, continually flowing. So it actually looks a little bit clearer here to me. And do you see all these lines here? This would have been like, there was deposition on the inside of the bank, and this thing was shifting more and more. Where's my camera? That way, that way, that way, that way. If I did that right. You're seeing like all of that deposition from the inside of each of these curves over a really long time. We're talking hundreds to thousands of years that this would take place over. It also clearly, as you can see, all these farms makes for pretty fertile soil. Rivers in general, because of the exchanges happening in life, death, photosynthesis, all of that stuff, tends to leave pretty rich organic material. So as that spreads out over the floodplain, it leaves pretty nice, rich, fertile soils. So we've gone and developed those pretty well. So yeah, there's the basics with meanders. It's just easiest to see down there. It's not that this doesn't happen in upstate New York. It does. It's not the Salmon River being controlled and having a lot of exposed bedrock. It's not as super easy to see in all the time, all the places. But go to turn on border so you can see this because the county border. There we go. The county border follows this little river right here, Chittango Creek, which flows north up into Oneida Lake, and you can see there's some in there. Meanders, meanders, meanders. And it's reasonably flat here. If you keep going south, you get into you go uphill pretty severely right here. This is a very very beautiful road, but pretty steep going uphill from Chittenango up to Cazenovia, and it follows right along the river. And you can see that the river's a lot more straight through there. There's a couple of bends where it flattens out, but it really just doesn't monkey around. Spends its time going straight downhill. Okay. All right. Let's check out some of these notes. So we usually write a whole lot here, but we won't. The golden rule, the thing that gets us through all of this erosion stuff, is this. When water speeds up, erosion takes place. Going faster and faster, it can pick up more and more particles. In fact, what we'll talk about up here, if you've ever had like mud on your car or something, and you put the hose on it, and it's not quite working, you put your thumb over a little hose hole to make the water go faster. And when it goes faster, it's more efficient at moving the mud off of your car, which is really what erosion is. You're making the water go faster. In fact, there's your erosion lab. We're not going to do one this year. You can say, I already did that lab. I've taken a hose and tried to get mud off of something, and I've had to make the water go faster to make that really work. That's erosion. You're doing it. This graph right here is going to show us that relationship, that the faster water goes, the bigger the particles it can move. So let's do this. This is a lot, but let's keep it short and sweet. Right? Easy to say 15 minutes into this. When water slows down, then, if you're, so take that hose, get the mud off of your car, and then it's washing down your driveway or whatever. When that water slows down, it can't carry that mud anymore. So it's going to drop it off. And that's what we call in earth science deposition. It's a little bigger so you guys can see it. Erosion and deposition. All right, so we usually write all kinds of stuff in here. I think I explained it on the other one well enough. But so let's just do a quick outsides of curves. Faster water. Erosion. Insides of curves. Slower water. Deposition. Again, remember is why we saw sand on the insides of all those curves. So this curve, if the water's going this way, I guess either way, if the water's going this way, this would be the outside of the curve. The water's going faster, it will erode, and this whole curve will migrate that way. The meander will get larger and larger and larger and larger. But then look, you got the outside of a curve here, you got the outside of a curve here, so there's erosion wants to take this bank and go that way, and this bank can go that way, so they meet up pretty soon. And you get a river with a separate Oxbow Lake, Oxbow. Cool. All right. So Floodplain, they're called meandering, Meandering. Sorry, Meandering, meandering rivers. All right. Higher in drainage basins tends to be steeper. Lower in drainage basins tends to be flatter. If you remember this whole deal, that we call an area of land drained by a stream system a drainage basin. So higher up, steeper, faster water, straighter streams. When you get down towards the bottom of the drainage basin, towards the mouth of the river, it tends to flatten out, and that's where you're going to get meandering and Oxbow Lakes and things like that. We may at one point make this diagram larger and do some stuff with it, but I think for now, let's just skip the bottom of that page. Call it okay. This is an unconventional year. All right. So the dirty car idea, when water speeds up, the rates and amounts of erosion speed up. So this reference table, this will be the last thing we do in this video, demonstrates this idea. The line is the line representing what speed of water it takes to move a certain particle diameter. Let's talk about a couple of things here, but let's jump in and just do one to see how it works. If my stream velocity is 1 centimeter per second, what I'm going to do is come down here to stream velocity. There's 1 centimeter per second right there. And I'm going to go up to the line. I'm in Cami, so let's draw it. You don't have to draw this on yours if you don't want. I go up to the line, I see where it hits. So right there is the spot, right? So this tells me at 1 centimeter per second, if I come over here, it tells me what size particles should be moving in that stream, which is sand. We can also get the actual exact size, but this gets a little funky because it's not a traditional linear scale like you're used to. It's one of these. We did these with the HR diagram. I don't know if you remember that. That's the one that had all the stars on it. But from here to here, the increments are they're not evenly distributed anywhere, right? It's easy to see here. If you go from 0.1 to 1, so that box is worth that much. Then from 1 to 10, that box is worth a lot more. Then from 10 to 100, that box is worth a lot more. So we do this to scrunch a lot of data onto a small graph, right? If we went from 0.0001 all the way to 100 on a linear graph, it would have to be like as tall as this room, which isn't practical. So you smush them down with these types of scales. Don't panic about it. If you can just ballpark it, generally Regents questions don't make you get like ultra specific down to the difference between 0.07 and 0.08. Like that's not going to happen. You don't have to worry about it. You've got to just be able to ballpark it, and you'll be all right. And if you can, if you're decent with graphs, you can figure it out. But don't panic about it. You're going to be okay. You'll be able to do it by estimating, essentially. But 0.01, 0.02, 03, 04, 05, 06, 07, 08, 09, and up to 0.1 then. So I'm going to say that's about 0.02. And again, the good news is that when you do this, it'll be multiple choice questions for the most part after you fight through this little chart here, which I'll make you do. All right. And then, like I always do, I make you fill out different ways so you have to do it forward, backward, everywhere in between. Let's think about one last concept and then see if we're ready just to jump in and finish those up. This stream, moving 1 centimeter per second, we just said that it can carry sands. Is that all it can carry? What do you think? It's certainly not going fast enough to carry pebbles, but if it can carry sand, it can also carry things that are smaller than sand, like silt and clay. So it's kind of like when you do this, it's the largest possible particle that would move, and then everything below it would be included in that, right? All right, so why don't you jump in and give these a try. I recognize that it gets difficult when the line gets really steep over here. I recognize that it gets difficult trying to say the difference between this line and this line. But really, again, as long as you end up giving me a value, if it's like right here and you say, I don't know. If you're between 1 and 10, you're good in my book. So just make sure that you're like in between those values and you'll be fine. Also, these dotted lines that separate out are 6 official particle sizes. And these are the real deal. If you ever see, well, like when we get into rocks, maybe they'll say something about pebbles. Now you know what a pebble is. A pebble is a particle that's anywhere between 0.2 centimeters and 6.4 centimeters. A cobble 6.4 to 25.6. So 25.6 and bigger is a boulder. That's not as big as like, I don't have a meter stick. Yes, I do. That's not maybe as, like, you think boulder, you're like, oh, but, you know, that's a boulder right there. You know, my head, boulder sizes. So, yeah. What do you think? I think that will be all we mentioned for now. Like last time, just save these notes. You should already have this weathering stuff done. If not, you got to go back and do assignment 2 before you're doing assignment 3. We're going to skip that for now. No worries. Why don't you try these questions? But what I'll do is, like I said, I'm going to set up a little classwork. These 5 questions will be part of that classwork. So you can try them now if you want to, low risk, and then I'll also put them on the sheet so that it's not confusing for folks. But those 3 will be on the sheet. That will be the classwork for this assignments. And this stuff will all be later. All right? That's erosion. No lab. Then we'll move into deposition, which there will be a lab for, but it's not so bad. Thanks for sticking with me, folks. You're doing great. We'll see you soon.